This is the island of Antikythera right here. It's between Crete and the mainland of Greece up here. This is Kalamata, where the olives come from. And this island is Kythera. In Greek mythology, Kythera was the place where the goddess of love, Aphrodite, rose from the waves. Well, Antikythera is this little island about halfway between Kythera and Crete. And in 1900, there was a storm, and Greek sponge divers who had been driven to Antikythera just to get out of the storm before getting wrecked, dived for sponges, and 138 feet, 42 meters down, they found an ancient shipwreck. This was just marvelous, and they went back again and again. This was a huge treasure trove, all kinds of statues, pottery, glassware, coins, and this thing, this lump of bronze and wood. They couldn't really tell what it was. Well, over time, this is in 1900, after being out of the water for quite a while, the wood dried out and it cracked. And in 1902, a Greek archaeologist named Valerios Stais noticed gear wheels in there. Well, this is just astonishing, because you think, is this really something that went down with this ship? Because we didn't know of the ancient Greeks or ancient anybody having geared mechanisms like this. 1958, half a century passes, and this man, Derek DeSoya Price, took a real close look at it. And here's some of what he saw. This is, let me dim the lights a little bit more so you can try to see this better. Not sure. Not that one. Let's dim there. Let's try that. See it a little bit better, I think, this way. This is the central gear housing here, front and back sides, close up, and you can see the teeth here on this wheel, sort of dimly. They're hard to see. They're pretty, 2,000 years in salt water will do a real number on bronze, or pretty much anything. Pardon?
Well, whatever you put in the water.
Yeah, yep, pretty much, yeah. This is the back side of the central gear. Here you can see these, the teeth on the gears, here and here. You can see them much better. And here's the right side, and again, you can see teeth on this central gear. This is all about the, there's a lot of gears in this thing, and we're not entirely sure how many, but we'll get to that after a while. And this is the left side of the central gear housing. And here is what looks like, this is where a crankshaft would go in there to turn it. And this is the door plate on it. And it's really hard to make out the markings on this, even in these excellent photographs. And the other wavelengths of light have been used to try to investigate this further. Here's some part, this is clearly a dial of some sort. Here is Greek writing. So after a year or so, DeSoya Price publishes this article in Scientific American, An Ancient Greek Computer. Time goes by, and he's still interested in this. He's still investigating it. A nuclear physicist in Greece, Charalampos Karakakoulis, makes X-ray and gamma ray images of the mechanism. Okay, these are much, much shorter wavelengths than optical light, visible light. Maybe we can see more and see through some of this corrosion that's encrusted the thing over all these centuries. A couple of years later, Price publishes Gears from the Greeks, and this was a long description in the Transactional American Philosophical Society. He concludes that it modeled the celestial motion, sun, moon, and planets. How old was it? Well, there was you can't test this thing directly. You think, well, could you carbon date the wood? I'm not sure you could. after being underwater all that time. Besides, you don't want to destroy any of it if you can help it. So you looked at the coins, the styles of the amphorae, the jars that surrounded it, the pottery and so on, all date to roughly 85 BC. This is consistent with the writing style of the inscriptions on it, made about maybe 100 BC, 15 years or so different. Where did it come from? Well, it was in a busy shipping lane from what we now term the Middle East and the island of Crete, going to Rome. This in 100 BC. That's the year Julius Caesar was born. Okay, it was not yet an empire in name, but it was pretty much in fact. Rome had extended its influence over much of the Mediterranean, and it had eliminated Carthage as its principal rival. It dominated the Greeks, and had been was invited into Palestine about that time to as a counterbalance to the Greeks, the Ptolemies. But anyway, it went down in this busy shipping lane, probably en route to Rome, and it carried luxury goods. This is what they found down there on the bottom of the ocean, including these vases in the style that was made on Rhodes. Okay, Rhodes, not the college, just a couple of miles away, but the island of Rhodes. A couple of very famous, well-known Greek astronomers lived there and had schools there in the 1st and 2nd centuries BC. Hipparchus, this is, if anybody could be said to be the father of astronomy, that would be Hipparchus. And we'll go into all of these ancient astronomers in a future edition of the short course later in the year. He is thought to have worked there for about 20 years until he died. And another man, Posidonius, later set up a school there, continued the tradition. I don't know whether he actually studied with Hipparchus or not, but here's some of the things that Hipparchus did. He applied numbers and accurate models to the solar and lunar motions, and we've just seen that's not an easy task. Now, they believe that all of these things revolved around the Earth instead of the other way around, which we now know to be true, but they could evolve models that actually worked, that predicted what they wanted to predict. He inherited a lot of astronomical observations from the Babylonians. They had done a great deal of astronomy, positional astronomy, and calculation going back several hundred years before Hipparchus's time. They did it because it was important to their religion. And Hipparchus did not do it because of religion. He did it out of a sense of curiosity, that the sense of sort of what we would term today an Enlightenment sort of view that many of the Greeks had. He compiled a table of trigonometry. He's known as the father of trigonometry. And he was probably the first, certainly among the Greeks, to be able to predict eclipses. So the Babylonians might have been able to do this as well. Records are kind of sketchy on that. He discovered the precession of the equinoxes. That's another thing that we will get into in another session. He made the first star catalog. All of these were just monumental achievements. Posidonius, who came a little bit later, tried to calculate distances to the sun and the moon. He calculated the distance to the sun. Well, he was off considerably on that, but still, it was a good try. He calculated the size of the sun. He got a little closer than others. The circumference of the earth using the elevation of Canopus. His estimate of the size of the earth was too small. It's because what he did was observe the elevation of Canopus. This is a star that it's the second brightest star in the sky, and it's almost due south of Sirius, the dog star, which is now setting about sunset. The only time you can see Canopus from here, from this latitude, is in the evening, is going to be generally in February. It's going to be a couple of degrees, maybe 2 degrees above the horizon. You've got to have a good horizon and really good weather conditions. I've seen it once, I think, from here, but it was more easily visible Then, from a similar latitude, again, because of precession, because the Earth wobbles a little on its axis, and things in the southern sky were higher at that time than they are today. But he used the elevation of Canopus as viewed from the island of Rhodes and then from the city of Alexandria. And he measured the distance between Rhodes and Alexandria and the difference in the elevation of Canopus as seen from these two locations. And then from that he calculated the circumference of the Earth. Well, it turns out his observation was flawed. He didn't account for atmospheric refraction, which they knew about, and he had a wrong value, an erroneous value for the distance between Rhodes and Alexandria. So there's no way he could be right, but it had enormous consequences, which we'll see in just a moment. He also believed that the moon causes tides. Now you think, hey, that's an advanced belief because nobody knew what caused the tides. Well, what he believed the mechanism to be was that the moon was composed of air and fire. Okay, you may remember that the ancient Greeks thought there were 4 elements that made up everything. There was earth, air, fire, and water. There was a 5th one called the ether, which was out beyond the corrupted influence of the earth and so on. But earth, air, fire, and water were the elements of which everything was made. He believed that the moon was made of air and fire and that it warmed the water. That made it expand sort of without boiling it. And so he was right for the wrong reason that, yeah, the moon does cause tides. Now, his calculation of the circumference of the Earth was about 18,000 miles. And Ptolemy accepted that as correct. Nobody bothered to try to replicate this. In fact, there was already a better measurement of the Earth it was Eratosthenes who did that, and we'll get to that also later, which is actually pretty accurate. Ptolemy accepted this circumference of the Earth as correct, and Columbus relied on Ptolemy, and he probably would not have made it, and I'm pretty sure that Fernando and Isabel, the king and queen of Spain, would not have funded it had they known that it was much farther away than Columbus predicted that India would be. However, this is one of these discoveries that's it's going to be made sometime or other. If it hadn't been Columbus, there would have been some other European who would have found the Americas, whether they would have gone from northern Europe to northern North America, or one of the Portuguese explorers moving from Africa, the relatively short distance across to what's now Brazil. Somebody would have found it, but it probably wouldn't have been this guy. Back to Posidonius. Cicero, or as he would have pronounced his name, Cicero, wrote about an instrument that he said, this is his description of it, that it reproduced the celestial motions. He saw one of these things, that it belonged to a friend of his who was the grandson of the Roman general Marcellus. Marcellus had led the Roman army that had sacked Syracuse, which was a Greek colony in Sicily. It sacked Syracuse in 212 BC. The famous Greek mathematician Archimedes lived in Syracuse, and Marcellus gave orders to his troops that if you find Archimedes, don't kill him. They were going to go through and do the usual loot, sack, kill everybody. And he said, don't kill this guy. But there was a Roman soldier who ran in, he saw this old man drawing something in the dust, and he ordered him to stop, stand up, give him whatever he had, and the old man ignored him, and so the soldier killed him. Well, that was Archimedes. And among the things that were looted from that city, of course, being the commanding general, Marcellus got his pick, and he picked out this device that Archimedes may have made, but at any rate was found with him or near him, took it back home, and that's what Cicero was describing here in in his statement when he had seen this thing at his friend's house. They kept it a couple of generations later. Now, we talked about lunar cycles a little earlier. There are several lunar cycles, depends on how you count. Metonic is named for the Greek astronomer Meton, who lived in the 5th century BC. This is a crater on the moon that is named after him. He observed, calculated that in 19 solar years, there are 235 synodic, okay, remember that, full moon to full moon, new moon to new moon months, and 254 sidereal months. Okay, remember what that was. The sidereal month is the moon against the same starry background. And we've touched on that, new moon to new moon, or the same location with respect to the stars. Callippus was another Greek astronomer. Here's a crater named for him on the moon. For Metonic cycles, he came later, less one day is 940 lunations, that is complete orbits of the moon, in 76 years, less one day. The Greeks could do mathematics with fractions, but it was very cumbersome to do it. They didn't have algebra, they didn't have arithmetic as we know it, they were geometers. And everything was done in a geometrical fashion. They did not have the numeral zero, they didn't have really the concept of zero, they had the concept of none, as in, yes, we have no bananas, but they did not have the symbol zero, and the Romans didn't use it either. And all of this made calculation more cumbersome. So they were looking for integers, whole numbers, with which they could calculate, because it made everything a lot easier. They tried to improve the prediction between these whole numbers of lunar months and the solar year, trying to come to that, that one where they all coincide, and then you don't have to fool with fractions anymore, which are, if you look at Greek numerical notation, they used the letters of the Greek alphabet. And then for fractions, they would use an apostrophe or a little mark on one side of it, and that could be interpreted in a couple, you could read it a couple of different ways. It was context dependent, kind of like the hyphen in sports writing, and you had to know the context. So if you could come up with a whole number, that was going to be much better. So Metonic versus Callipic cycles, comparing both to the tropical year, that is summer solstice, summer solstice. That's how the Athenians calculated their year. They started their year on the summer solstice. Well, that's a convenient time. We start ours on January 1st, which is near the winter solstice, but not quite. You can start, the solstices and the equinoxes are the favorite times to start years, because those are points that are very clear clearly observed, easy to observe, and mark the change of seasons almost. Well, in predicting the tropical year, the Metonic cycle is too long by about 6.5 minutes. The Callipic cycle is too short by about twice that, but they didn't know that inaccuracy around 100 BC. That was actually pretty close estimate. Now, the Saros. This is kind of the key to understanding the eclipses. The name, by the way, Saros, comes from a Babylonian word, sar or saru, which means 3600, and it was adapted. The 3600 was, I won't say a prime number, because that's a different sense of the word prime, but it was an important number to the Babylonians. Their math, their arithmetic was base 60. And so things in multiples of 60 were important. The person who first applied the word Saros, kind of making a Greek term out of it, was Edmund Halley. 1691 was first to name this cycle, the Saros cycle. The synodic month, okay, we're going back just to rehash a little bit, new moon to new moon. The Draconitic month, okay, there's a different kind of month. Draconitic is node to node. That is when the moon, again, the moon's orbit is tilted about 5 degrees, 5, 6 degrees to that of the earth, and the node is the point at which that orbit crosses the Earth's orbit. So when the moon moves from one node to the other, that is the Draconitic month, and it comes from the Latin Draco, meaning dragon, because in looking at an eclipse, it looks like people would talk about a dragon eating the moon, okay, taking a bite out of the moon. So this Draco the dragon did not live by the sea or frolic in the autumn mist with anybody, but that was the Draconitic month. The anomalistic month, that's another kind of month, perigee to perigee. That is the closest point in the moon's orbit to the next time it reaches that same point in its orbit, the closest point to the Earth. Now, here's where you get into these equivalencies. 223 synodic months, new moon to new moon, is about equal to 242 draconitic months, which is about equal to 239 anomalistic months, plus or minus a couple of hours, or it works out to 18 days, 11 days, and 8 hours. That is the Saros cycle. Now, after one of these cycles, because of all of those equivalencies, again, look back there, these are all, when all of these sort of coincide, then you'll have the moon at the same phase. It'll be at the same node, okay, the same crossing point of the two orbits. It'll be the same distance from the Earth, and that means that the Earth, moon, and sun geometry will be almost identical to the previous time. And we'll talk about that, and I'll show you a little more about it in a moment. Now, so that if the date of one eclipse is known, one Saros later, 18 days, what was it? 18 years, 11 days and 8 hours later, one Saros later, a similar eclipse should occur. So you're going to predict an eclipse. But it's not an integer number of days. Here you can see Callippus and Posidonius saying, "Dang!" It's not an even number of days. It's a fraction of a day, about a third of a day. Well, a third of a day, a third of 24 is 8. Okay, roughly 8 hours. Therefore, because of the Earth's rotation, at each successive Saros cycle, the eclipse will happen about 8 hours later. So it'll be about 120 degrees to the west. Okay, why 120 degrees? Because that's a third of a rotation of the Earth. 360 divided by 3 is 120. And after 3 Saros cycles, or 54 years, 1 month, or almost this many days, the eclipse will happen at almost the same time. All these coincidences, and people were observing these things thousands of years ago, but people had to be really observant, had to keep really good records to tie all this down and then pull it all out and consolidate it and make it into something that would predict. Now, 3 Saros cycles, this number here is known as the triple Saros, or in Greek, exoligmos, the turn of the wheel. And we'll get back to this in regard to the Antikythera device. All right, here is Saros number 136. I'll get into the numbering of Saros cycles here in a moment. Let's go back to the first one of these. You'll see here 1937, okay. 1991, you see where it is. It's a midpoint, say somewhere below Baja California, but out in the Pacific Ocean. 1955, 18 years later, here the midpoint's a third of the way around the Earth, 120 degrees around the Earth. So it's down in the Indonesia area. And 18 years later, another 120 degrees around the Earth, it's in Central Africa. Well, and the next one, 18 years after that, would be 1991, all right? Almost back below Baja California, but it's moved a little north. Then another 18 years, another 120 degrees westward. It's moved north. It's roughly the same, the same longitudes. And then another 18 years later, 2027, here's where it's going to be. Another 18 years, 2025, 2063, 2081. So you see, they're moves westward like this, 120 degrees approximately at each iteration of this. It's also moving north. What's with that? Now, this is not supposed to have happened. I hope we can still read it. It looked okay when I had all this at home. each succeeding eclipse goes progressively north or south with respect to the center of the Earth, depending on where it started. Now, the eclipses can start toward the poles, and if they do, when they do, then as that eclipse cycle progresses, it's going to move progressively north or south, depending on where it started. Now, they last, and this is really hard to read, and I'm sorry for this malfunction, but anyway.
I was looking at it, it did that, but when I advanced it, I think it cleared up.
Let me
Something happened.
try it again.
Yes.
Okay. All right, now, there we go. Saros cycles last for a really long time, but not forever. Any given Saros cycle is going to last sometime between about 1,200 and almost 1,600 years, or this many eclipses. And of those 80, 60 to 87, about 40 will be central eclipses, and the rest will be partial. Now, here's the numbering, and this is arbitrary. Okay, there's no astronomical reason that when they take place near the ascending node, they have odd Saros numbers. They just decided to do it that way. And taking place near the descending node, that means the ascending node means when the moon is coming up across the plane of the Earth's orbit. Descending is going down. The node is on the other side. It's going down with respect to the Earth's orbit, and they have even numbers. That's just a way of keeping track of it. And this was introduced by an amateur astronomer. And this was in 1955. There's a lot of us who were living then. And George Vandenberg was an amateur astronomer. He was a lawyer by training. But he has wound up, he was fascinated with eclipses and the Saros cycle. And so he introduced this numbering system, which is now adopted worldwide. So, you know, amateurs in astronomy, we do it because we love it. That's the basis of the term, amateur, the Latin word amare, to love. We do it because we love it, but you can still contribute to astronomy as an amateur. It's the last science to which amateurs can make significant contributions on a large scale. Just a little plug. Now, this is the Saros 145. That's the cycle of which the upcoming eclipse in 2017 is part. That's this one here. Well, this one this Saros cycle started in 1639. They were all of the eclipses until 1891 were partial. And then in 1891, there was an annular eclipse. That's the annular eclipses have the sort of open, I guess more nearly closed, or narrower lines is what it is. Anyway, this is 1891. There was this eclipse close to the North Pole. Okay, 18 years later, that would be 1909, there was another one. Here's central eclipse, central part of the eclipse. And then another 18 years would be, 1927? Yeah, there it is, 1927. And you see this is moving far north, moving a little farther south, 1927, 1925, and so on, 1963. And so you get on up here to, this is the one that's going to go across Nashville, or right here is Hopkinsville, Kentucky. Right there, Nashville is going to be right here. And this is the one that we will be able to see. And then here's where its follow-up is going to be, 2035. It's going to be over here, 2053, down here, and so on. This cycle will go on until the year 3009 will be its last gasp. And the last total eclipse, the last central eclipse of this series, I believe, will be in about 2700 and something. I forget the exact date. But anyway, these things last a long time. And here you can see it started toward the north, and each successive one, it moves a little to the south, and it also moves about 120 degrees or 8 hours around the Earth. Now, back to the Antikythera mechanism. This is a reconstruction of it. A guy named Tony Freeth put this together, published this in Nature in 2006. And here's a schematic of it. I'm not going to go into a lot of detail on this, partly because I can't. It's just beyond my ability to describe it. I'm not a mechanical engineer, and here you see there's some lost epicyclic gearing in here. They know that we don't have the whole thing. So they put it together based on what we do have, plus some inferences. But here are the cycles. We've got on the front dials, you've got the zodiac. This is where the readout part. The Egyptian calendar, they chose that for reasons that it had to do with simplifying things. And the parapegma is kind of like the Old Farmer's Almanac, the Greek version of that. It was originally in stone, and it was holes drilled in stone, and you could put a peg in there day to day over the course of the year, and from that you would be able to make some sort of educated guess as to some of it would be educated, some of it so what the star background would be, constellation, but also the weather, things like that. I had a friend ask me, a friend at Shelby Farms, I volunteer out there, and a friend asked me sometime back if I had a copy of the Old Farmer's Almanac. I said, well, no. Why do you ask? And she said she wanted to know, this is in the winter, like, January. She wanted to know what the weather was going to be on September 11th or something. And I said, well, I don't know, and neither does the Old Farmer's Almanac. If it gets it right, it's a lucky guess. All they can possibly do is look at weather patterns and make an educated guess on the basis of that. I mean, think about how hard it is to make an accurate forecast a week in advance from weather data. So no, but she wanted to have that Old Farmer's Almanac, and she still wants to have that Old Farmer's Almanac to plan events. Go figure. But the parapegma was that sort of thing. It was a predictive device for weather as well as for what you're going to see in the sky. Down here, you've got the cycles, okay? There's the Ecliptic cycle on this set of gears, the Metonic cycle times 5. This is the lunar-solar calendar. This is the back dial. The Saros over here, the Exoligmos, that's 3 Saroses, and the eclipse prediction back here. Pin and slot. This was an ingenious mechanism because it allowed for representation of the moon's varying distance from the Earth. Okay, because they did not recognize that its orbit is an ellipse, but they knew that the moon was sometimes farther away or larger in the sky than it was at others. And so this thing had, every time it turned, there would be a pin and a slot would move, and it would force the other gears to turn in a way that it reproduced the moon's motion. Here's the gearing system, the gearing ratios. Okay, the Metonic dial, 5 turns in 19 years, and here's the gearing. You can see all the B2 and all this. I don't really understand all that, and that's okay. I don't have to. But here's the ratio. It all works out to 5 turns in 19 years, and this estimate is based on counting the gear teeth when they could. And they could not always do it. Again, making inferences. So some of this. You say, is this an exact reproduction of the Antikythera device? And the answer is probably not, but it's probably pretty close too. Here is a computer schematic of it, reconstruction of it, the Saros cycle over here. These are the gears, the Ecliptic cycle, the moon pointer. This is not in the case. Then here's the offset wheel for the moon's 19-year cycle. And here's kind of an exploded view, the front door inscriptions, parapegma inscriptions, the back door inscriptions, back plate, and all of this stuff. And here is Derek DeSollier-Price. He made a much simplified reproduction of the Antikythera device. And here is Michael Wright. He put together one that is probably pretty accurate. We'll see about that. Here's what it looks like. This is a photograph, front view and the rear view, and the question is, does it work? Well, let's go to YouTube and we'll see.
This is a reconstruction of a 2,000-year-old computer. The original battered pieces were found in a shipwreck more than a century ago, and Michael Wright, a museum curator from London, spent decades studying them in order to work out what the device was for. He built this model in his home workshop, with techniques similar to those that the Greeks might have used.
This is my model of the Antikythera mechanism. The mechanism is a box full of gear wheels, driving indications on dials, one at the front and one at the back, which we'll look at in a moment. And it's all driven by working from the hand knob here. On the front dial, we've got two scales. The inner ring is the zodiac divided into degrees. The outer ring is an annual calendar scale, 365 days.
The device is a machine for predicting the motions of the heavens. When you turn the handle on the side, pointers move around the front dial, showing the movements of the sun, moon and the 5 planets that the Greeks knew. The fastest pointer here is for the moon, going around the sky once a month, while the white and black ball shows its changing phase. Inside, a sophisticated setup of wheels riding around on other wheels models the varying motions of the planets, according to the Greeks' astronomical theories. As the side handle turns, the planet pointers sometimes move forwards and sometimes backwards. Meanwhile, the sun and moon pointers vary in speed, just as the actual sun and moon do when seen from Earth.
Now we'll look at the back. We've got two sets of two displays together here. The upper one is basically a calendar. The spiral scale is divided into months, each of which is named, and this is a cycle of months, 235 months, which fit into 19 years. These are months measured by the moon.
An extendable pointer with a little needle on the end tracks the spiral groove, just like the stylus on a record player. When it gets to the end, you can lift the pointer up to reset it. One of the little dials just inside the spiral shows the dates of the ancient Greek games, including the Olympics on a 4-year cycle, while the other tracks a much longer 76-year cycle.
The lower display is giving the times at which there may be eclipses. Again, it's graduated into months, and the markings are just in those months in which we expect there to be an eclipse either of the moon or of the sun or of both. The thing about eclipses is that they happen according to a pattern which repeats after 223 months. So here we have a 4-turn spiral scale with 223-month divisions.
This dial is one of the most exciting parts of the mechanism. It was used to predict eclipses of the sun and moon according to a repeating 18-year cycle. The Greeks probably got the data from ancient Babylonian astronomer priests who had been observing eclipses for centuries. Inside the mechanism, you can see the gear trains that drive the pointers on the back dial. This shot also reveals that this model was made of recycled metal plates, just like the original would have been. This is the first model of the Antikythera mechanism to incorporate all of its known features. Thanks to Michael Wright, it's working again for the first time in 2,000 years.
Okay. Are there questions? Thank you.
Question.